My name is Shireen Chan, and today I'll be talking about depth estimation, or more specifically, the magic of depth estimation. Quick intro about me. I work as a computer vision intern at eNord. It's an autonomous drone-based startup. I have worked previously with Omdena on a few of the projects, and currently I also contribute to a lot of open source libraries and organizations. And I'm an avid Netflix fan, so you'll always find me seeing Netflix. So let's begin. So what exactly is depth estimation? Seeing the words itself, depth and estimation, it literally means estimating the depth. And in terms of computer, it means to calculate the distance of each pixel in an image from the camera, or a video as such. Once we estimate the depth, the result that we get is a map which depicts the depth, the distance of each pixel in the image from the camera. So if you can see the examples here, so in the first one we have a car moving around, and the second one is a camera moving around the house. So in the first one, if you see, as the car goes further, the color of the car becomes more darker. So at the beginning it was white, and then it starts becoming darker and fades into the background, showing its depth. Similarly for the bottom one as well. So how exactly does it work? And we'll start from the basics itself. So do you all know how does a camera work? So right now the camera that's shooting me, how do you know it's how does it work? How is it capturing me? Does anybody know about it here? Okay, so basically what happens is light that is reflecting from me, so the light falling on me is getting reflected and gets captured by the camera here. So light falling on me, I bounce the light back, and the camera captures those lights on its photoreceptor cells. And that's exactly how a camera works. So if you can see in the diagram here, I have my 3D scene here, and light coming from the 3D scene is captured by a camera and forming a 2D digital image. Now, given the same situation, given the same point, given the same arrow, the line itself, can I go from a 2D image to a 3D scene? Of course we can. So if given the point and the projection ray, the line itself, we can trace back from the point to the 3D scene. So the red point that I have here and the line, given those lines, I can just trace it back like this. But the problem arises here. I don't know where to stop. I could stop at the blue point, I could stop at the green point, or I could stop at the yellow point. I don't know where to stop. We have the X points, we have the Y points, we don't have the Z. The Z here being the depth. I don't know how far along I need to stop at to figure out where exactly in the 3D scene my 2D point lies. And for solving this particular problem, we use a term or a pair of images called as stereo pair. A stereo pair is a pair of images that are captured by two cameras. So I have my camera A here, and I have my camera B here. And both are located at a horizontal distance from each other. But sometimes, due to unavailability of two cameras, we can also make this work with one single camera. So I have my camera here, I click a photo, and right after that, I horizontally displace the camera and click another photo. So in short, we're trying to achieve two images here, and that pair is called a stereo pair. So let's visualize this better using an example. So we have a left image here taken by a left camera. We select a point on the left image, the red dot that you can see. So we have an image, we have the red dot. Where do you think the corresponding 3D point will lie? As I mentioned before, as we established before, that the line that we take out from the point, the same line that we get when we capture a photo from a camera, the light that is reflected, given that ray and given that point, we know where the corresponding 3D point will lie. But we don't know how far it will lie, right? So for solving this particular problem, we use our weapon here, our friend here, that's the right image. In similar fashion, we find the corresponding point. The point that we found in the left image, we find the same exact point on the right image. I'll get back to how we found this point in the later slides. But suppose we do find the same point in the right image as well. We take the same, we give them names UL, VL, UR, VR, and take the same ray from that point, backtrace it. So now you have two rays. You have the one from the left image, one from the right image. And as you can see, the point where they intersect is the location of the point in the 3D scene. Reiterating it again, so I have my left image here. I have my ray that was there that we got from the camera. Then we take our weapon here, the right image, perform the same procedure here as well. And the point where these two projections or two rays meet is the point of the location of the point in the 3D scene. So just giving them a few names like ULVL, URVR, and XYZ. This particular technique that which I showed you right here is called as triangulation. And this whole system, this two images, two cameras, getting the rays and everything, is called as stereo vision or a stereo system. Right now, your two eyes also take use of this particular system. So people who are sitting in front of me, they know I'm closer to them because they're using their two eyes. You have a left eye and a right eye, which acts as a left camera and a right camera, performing similar actions like this triangulation. So, going back right here, so getting a little bit into geometry here, I have my points, I have my lines. How do you find the point where they meet? Using basic geometry, we would solve simultaneous equations and get the point. That's the location, the XYZ. If you do go and solve it, you will find that the XYZ points look something like this. So ignoring the numerators over there, the denominators here are UL minus UR in all the three places. This particular distance this is the distance between the x coordinate of the left image and the x coordinate of the right image. And this particular distance is what's called as disparity. Disparity is the thing that helps us estimate the depth of a pixel from the camera. How do we get the depth? Disparity is inversely proportional to depth. So, going through the whole process again, you have your left image, your right image, you try to find the intersecting point. On finding the intersecting point, the formulas that I showed you, you calculate that, and the denominator that you get, that's UL minus UR, is your disparity, which is inversely proportional to depth. So before I actually got into the process, I talked about selecting a point on the left image and the right image. This particular problem is called as a correspondence problem. So how do you suppose we find the pixel on the left image and on the right image? How do you find the same pixel? Can anybody take a guess at it? So what we do is we compare that chosen pixel with every other pixel on the right image, every other pixel. But that's computationally inefficient. That's not how things are supposed to work as. And hence, that's why we use our brains, we use a thing called brains that we have here. Since we displaced the camera, if you remember, the left camera and the right camera were horizontally displaced. They were at the same level vertically, but horizontally they were different, right? So using this knowledge, we could know that the pixel on the left image has to lie on the same line as the pixel on the right image. It won't be up or it would be down. It is going to be on that same level as of the left image. And that's exactly what we use. Instead of comparing with every other pixel on the right image, we just compare it with the pixels on that same line in the right image, and we find out the corresponding point. So I'm going to be showing you a demo. Nothing's good without a demo. So you can scan that. You can scan that on your phones right now as well. So this particular demo was built using Gradio and was deployed using Cloud Run. So I talked about what is depth estimation. I talked about how to use how does depth estimation work. But where exactly can we use depth estimation? Like, what are the uses? So the first use that I think all of us know about is 3D modeling. 3D modeling here is something, if you all have actually gone through, Google Maps uses this, something called as immersive view, where you can take a view of the whole city while locating yourself. So that's exactly the place where Google uses depth estimation. A few years before, I think, Google had come out with a Kaggle competition as well about registering images to actually form that immersive view, to actually build that immersive view. So that's exactly where they use depth estimation. Then we have object tracking and autonomous vehicles. So our most beloved car, Tesla. Tesla uses depth estimation Tesla cars use depth estimation to figure out how or like on the self-driving cars, they help to figure out how close a car is, or how far a pedestrian is, how far an object is, if there's a turn, if there's a building. All those stuff is determined using depth estimation. But the thing that they use over there is called as monocular depth estimation instead of stereo vision depth estimation. Stereo vision requires you to use 2 images, and hence requires 2 cameras, or requires 1 camera taking images sequentially, which is time-taking. So in these self-driving cars where you need a faster response, where you can use only 1 camera as such, we use monocular depth estimation. What exactly happens here is we use a deep learning model here, which is already trained on data sets having the image and the respective depth maps. So that's exactly what's used in autonomous vehicles as such. Then another big use of depth estimation comes in medical imaging. So what exactly is medical imaging? If you've actually researched about healthcare and as such, AI in healthcare, you'll notice there's this one recurring problem that occurs in the healthcare sector, that's doctors not being able to visualize the problem of a patient properly. They will always have to get into surgery to visualize what exactly is the problem. And to avoid that, we could use depth estimation. So for example, we have a patient who has a tumor. Using depth estimation, you can figure out how deep the tumor is, how big the tumor is, what's the mass of the tumor, is it benign, is it malignant, and all sorts of things. So that's where we can use depth estimation in medical. And finally, the last one, mostly in the entertainment industry, the human-computer interaction. So how many of you all have actually played with the Oculus before, used the Oculus before? Great. So if you've actually experienced that environment, you'll know that the controllers that you use depth estimation to figure out where and what object are you pointing at. So if you actually get a chance to explore, use Oculus, you'll realize that depth estimation is used everywhere in Oculus to get that immersive experience. So we saw the working of depth estimation. We saw what is depth estimation. We saw where depth estimation is used, and we saw it in demo as well. So looking at all the and currently there's a lot of research and development that's going on, and exciting future applications are coming in. So not only in just the healthcare industry or in your entertainment industry, but there are various other industries where depth estimation is propping up. So looking at all these examples and working, we can say that computers can for sure see beyond the surface. And this, my friends, was the magic of depth estimation. Yeah, so that was my presentation. Thank you guys for being an amazing audience. Thank you for the questions. Hope you liked it. If you all have any other questions, suggestions, or you want to collaborate, you all can hit me up over there. So thank you.